So now we're going to look at calculating limits. So we've seen graphically how to determine limits, but how do we calculate limits analytically? In other words, if we're given a function and asked to find the limit as x approaches some point, how do we do that without a graph? Okay, so the way we're going to do that is we're going to start out with some basic limits. Some limits that we can really decide how to calculate really on our knowledge of the graphical meaning. So let's look at this first one here. The limit as x approaches a of k, where k is a constant. So let's think about what this would mean as far as a graph. So if we had the constant function k, all right, that would be something like this. Maybe f of x equals k for that value k. So it actually doesn't matter what a we're talking about. If we're approaching a, then the function value is always k, so it has to be k. All right, so the limit as x approaches a of a constant is that constant. All right, how about the next one here? Limit as x approaches a of x. All right, now we have a slightly different function. We have the identity function. So we have the function f of x equals x. All right, and so if we're talking about some point a, and we approach a from the left and the right, that would mean we would be approaching it like this along the function. But because this is the function f of x equals x, or in other words, y equals x, this value over here is a, because x equals a is going to give you f of x equals a. So this is x. I'm sorry, back up. That is not x, that is a, because basically we're taking x to approach a and asking what x is as it approaches a. All right. So the next two really follow off that same idea. I won't do the graph of them, but the limit as x approaches a of x to the n is just a to the n. And the limit as x approaches a of the nth root of x is the nth root of a when defined. Okay, so you may be seeing from some of the previous ones that it seems like we're kind of just plugging it in. Keep that thought for a second. We'll get to that idea soon. But let's take a look at some examples based on what we were just doing. All right, the limit as x approaches 4 of 3. So x is approaching 4 of the constant function 3. But that function's always 3, so it's just 3. Limit as x approaches negative 2 of x. Well, that's just the function x. So as x approaches negative 2, we get negative 2. Limit as x approaches 4 of x to the third. That would be 4 to the third, or 64. The limit as x approaches negative 8 of the cube root of x would be the cube root of negative 8, or negative 2. And there we go. So now we have some basic limits that we can calculate, but we need to know how to put them together, how we can combine them. And that's where the limit laws, or the properties of limits, come into play. This will allow us to combine different expressions and do the limits of larger expressions based on what we already know. All right, so let's just start with if capital L, capital M, little a, and k are real numbers, and the limit as x approaches a of f of x is L, and the limit as x approaches a of g of x equals m. So what we're saying is that as x approaches a of f of x, we get the limit L. And as x approaches a of g of x, we get the limit m. So one thing to note is that in this case, both limits exist. Okay, so that's going to be important because to apply these properties, we're going to need that both limits exist. We do know their limit. We do know they exist here. One is L for F and one is M for G. Okay, so then we get to this first limit law. The limit as x approaches a of f of x, either plus or minus g of x. Well, a lot of mathematics, a lot of calculus is about what order can things be done in. So this is saying basically we're going to add or subtract f and g and then take the limit. But we'd want to know, can we take the limit of these things individually and then add or subtract them? And in this case, because the limits both exist, we can. So this would be the limit as x approaches a of f of x, and then plus or minus, whichever one you're doing, the limit as x approaches a of g of x. And from what's above, we know that that would come out to be L plus m. All right, and what this is the sum and difference rule for limits. Okay, what's next? All right, maybe we want to multiply f and g and then take the limit. We'd like to know, can we instead take the limit of f, take the limit of g, and then multiply them? In other words, instead of multiplying and then taking limits, can we do the limits and then multiply? And in this case, since they both exist, we can. The limit as x approaches a of f of x times the limit as x approaches a of g of x, or in other words, L m. Okay, and this is the product rule for limits. It's going to be important for us to use these terms, use these sum, difference, product, because a lot of the rules in calculus have to do with when you have a sum, when you have a difference, when you have a product, when you have a quotient. So get used to saying these things. You have a product here, you have a sum or difference here. All right, here we have a slightly different product. All right, the only difference in this one is this k here that's multiplying f of x is a scalar, a constant. Okay, so what we want to know is we're going to take f of x, multiply it by k, and then take the limit. We want to know, could we actually sort of factor out that k? Yes, we can do k times the limit as x approaches a of f of x, or in other words, that would come out to k L. So that's the constant, or sometimes called scalar, multiple rule for limits. All right. What about some other combinations? We have a quotient. We're going to take f of x divided by g of x, and then take the limit as x approaches a. So can we do the limits first and then the quotient? In this case, yes. Limit of f of x over the limit of g of x, both as they approach a. And that would be, based on what we've been told, L over m. Now, we do have to worry about one thing here, because remember, anytime we have something in the denominator, we want to make sure it's not 0. So this would be assuming m is not 0. All right. We'll get to that later on of what happens if we do approach 0 in the denominator. Okay, and this was the quotient rule for limits. Okay, and then finally we have the limit as x approaches a of f of x to the n, And so we actually can do the limit as x approaches a of f of x, and then take that to the nth power. So we would get L to the n. We could call that the power rule for limits. And that was kind of assuming that n was a positive integer. Now, we could also do some sort of fractional, some sort of rational power here. And so it could be doing the limit as x approaches a of f of x, and then raising it to the n over m. And I get L to the n over little m. All right, and assuming that quantity is defined. So we might be taking even roots of negative numbers, which we can't do in the reals. Okay, so, and this is the, we could call it the fractional power rule for limits. Okay.